So we enter the thermal properties section. This part asks how lattice vibrations affect the way a solid stores thermal energy. When temperature changes, the vibrational activity changes too. Suhu naik, vibration akan naik. Okay? The phonon also will increase, the frequency will increase. So that changes the internal energy and the heat capacity of the material. Kan? So naik, vibrational activity akan change. That vibrational, the phonon activity will change the internal energy and the heat capacity of the material. So from this point onward, we are going to connect phonons with measurable thermal behavior. First, we will discuss energy distribution. Then we will look at the density of vibrational states. And after that, we will study the Einstein model and the Debye model. And finally, we will compare how well they describe real solids. Okay, this one. Ya, saya maximize yang ni. Kenapa dia macam ni? Alright, okay, good. To understand thermal properties, we must understand how vibrational energy is distributed. Phonons follow Bose-Einstein statistics. What is Bose-Einstein statistics? Oh my. So that means the way they occupy energy states is different from classical particles. At low temperature, only a limited set of vibrational modes are strongly active. As temperature increases, more vibrational modes becomes populated. That is why the internal energy of the crystal increases with temperature. Yeah, temperature increase, internal energy akan increase. Why? Because phonons follow Bose-Einstein statistics. And why is that? Because the way they occupy energy states is different from classical particles. At low temperature, only limited set of vibrational modes are strongly active. Temperature increase, more vibrational modes becomes populated. Kan? Maksudnya mungkin vibrational mode akan ada begini dalam suhu rendah. Naik je suhu lagi, dia ada gini, dia ada gini. Naik lagi suhu, dia ada gini, dia ada gini, dia ada gini. Naik suhu lagi, dia ada gini pula. Dan so many vibrational modes. Nanti saya akan tunjukkan satu simulation, tunjuk you how many vibrational modes can we have in certain crystals. So the detailed expression on the slide is really just a mathematical way of saying detailed expression dekat dia punya all those equation. Please do not memorize the derived formula. No. Do not memorize this formula. Do not. Okay. We are just showing that the thermal energy stored in solid depends how many vibrational modes are excited and how strongly they are occupied. And how do we do that? How can we calculate? How do we know how many vibrational modes? We don't use manual calculations. We can, but it will be a very lengthy one using that equations. No, we are not going to do that. We are material technologists. We have softwares for that. The software, the Gaussian 09W and the Gauss View 5.0. Please install. Make sure you install that. And from that software, we could calculate how many vibrational modes and how strongly they are occupied. This is just a simple way of saying of the idea of temperature increase, internal energy increase, and vibrational modes also due to vibrational modes increasing vibrational modes. Itu je kita cakap. From that all of that equations. That equations not for us. It's for pure physicists. We are material technologists. We will use the software later. Now, Alamak, asal tak keluar? Oh, missing one. So this is 18, 19 is missing. Okay, I stop for a while. Later I continue. 19 is missing. Why slide 19 is missing? Oh no, we have slide 19. Never mind, I use this one. I use this one. Paksa guna gini lah. Right. Harap-harap you nampak lah. Okay, still nampak Right. So slide 19 Now we come to the density of states. Oh, apa pula density of state ni, sir? So density of state is one of the most important concept. Everything is important. Sir dah cakap everything is important. So density of state is one of the most important concept in thermal physics. So the DOS, density of states, also known as DOS. Okay, density of states tells us how many vibrational states are available in a given frequency range. The vibrational state that we mentioned in the previous slide, okay, density of states will tell us how many vibrational states are there at any given frequency range. Contohnya, 1 Hz, mungkin ada 1 Hz macam ni, 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 dan sebagainya. It will give us a number. So this matter, density of state is important because thermal behavior depends not only on the energy of a mode, but also on how many such mode exist. Kalau ada satu je, not much contribution to the total overall thermal properties of material. Kan? Ataupun if the frequency is small, but we have few thousands of that modes, ada few thousands yang vibrating at that modes, so it will contribute a lot to the properties of the material. So the DOS is like a counting function. It tells us where the vibrational opportunities are concentrated. If many states are available at certain range, and that range can contribute strongly to the thermal properties. So this idea becomes essential when we build the Debye model. Okay, sekarang saya cuba play slide semula. Why lah slide number 19 hilang lah. Ada pula. Ke sebab ramai sangat pakai I don't know lah. Ada pula slide 19 ni. Cewa. Okay, we look at slide 20 lah. Slide 20. Alright. Now, tadi kita sudah tengok Debye model kan untuk acoustic branch. So now untuk Einstein model pula, dia adalah sebenarnya the earliest successful quantum model for the specific heat of solids. Specific heat. Tadi kita sebut internal energy. Try to Google what is internal energy. Nanti saya tanya juga. Sekarang we are talking about specific heat lah. What is specific heat? Kan? So its main assumption is very simple. All atoms vibrate with the same frequency. Itu assumption of Einstein. In the early days, it is one of the successful quantum model lah, Einstein. Well, that is clearly an approximation. Kita main macam apa? Pengumuman bahasa Melayu. Approximation macam the main menganggaplah semua macam ni kot, lebih kurang kot. Macam that is an approximation. But it makes the problem easier to analyze. The important achievement of the Einstein model is that it improves greatly on the old classical prediction. At high temperature, it approaches the expected classical result. Pada high temperature lah. Tapi at low temperature, it predicts that the specific heat decreases, which is much more realistic than the classical model. But however, it is still limited because real solids, they do not have only one vibration frequency. So the Einstein model is an important step forward, but not the final picture. Real solid, we are learning the solid state physics, and in solid, especially semiconductor, they do not have only one vibration frequency. We have so many vibrational frequency depending on the structure of the crystal. Nanti kita akan tengok, we will try to simulate one quantum dots, and from that simulation we could see the mode of vibration, the vibrational frequency, and we could count how many how many atoms vibrating in that frequency range. From that one, we could predict what kind of thermal behavior does a quantum dot should have. Nanti kita akan tengok. Mana lagi? Debye model, spectrum and cutoff. Okay, so now Debye model improves on the Einstein model in a major way. Debye menambah baik model Einstein dekat banyak cara. So instead of assuming one single vibration frequency, it allows a whole range of frequencies. Kan Einstein salah, dia anggap frekuensi dia sama saja, one flat line, but no. Debye kata dia sepatutnya macam ni. Kan? But Debye pun ada limit, yang mana pada K besar sepatutnya dia tak akan naik lagi, dia akan curve, dia akan bend. Begitu. Debye model treats the low frequency acoustic vibrations as if the solid were at continuous elastic medium. At the same time, it introduces a cutoff so that the total number of allowed modes remains correct. So the Debye model is more realistic because it includes a spectrum of vibrations rather than only one. That is why it explains low temperature thermal behavior much better. Itu Debye model. At low K can be described by Debye model, and at low temperature also can be described by Debye model. Low temperature, not high temperature. Starting from Einstein, we move to Debye model. Okay. Ini yang kita baiki ni. Nanti saya akan bagi paper yang mana kita baiki Debye model. Now this slide connects the Debye model to the density of state, Debye and DOS, and then to the heat capacity. So the physical logic is simpler than the mathematical looks. So first we count how much vibrational modes are available at different frequency. We have set of frequency and we count how many vibrational modes available at that frequencies. Second, we determine how those modes are populated at given temperature. Pada temperature sekian, what modes at what frequency. Temperature naik, macam mana statistics dia. So third, we combine that information to find the internal energy. This also can be calculated using the Gaussian and Gas view 5.0, but we don't want to do that in this course. In this course, nanti kita cuba modelkan satu crystal structure saja. I think that will be enough. Kita jangan pening-pening pada kira heat capacity, internal energy. We don't do that in this course. Nanti you pening. Jangan kira banyak. Dapat kita buat yang nampak gambar lah. Kita modelkan quantum dots ke so on so forth. Apa lagi? Okay, we can find the internal energy. So after we have calculated the internal energy, we can determine the heat capacity. Itu dia punya kaedah. That is the methodology. Again, first, count how many vibrational modes available at different frequency, and then we determine how those modes are populated at given temperature, from low temperature to increasing temperature. Third, combine the information from the first, second step to find internal energy, or U. So after we can find the U, we can determine the heat capacity. That is all. Because U is related to heat capacity. I know you have learned physics in your year 1 kan. Mungkin ingat tapi terlupa rumus dia. But they are related. So even though the equations looks long, the actual idea is straightforward. Count the modes. See how strongly they are excited and then add their contributions. That is the heart of Debye approach. Macam tu apa yang Debye buat. Now, tak apa, sikit lagi ni. Nak habis lah. This one. Debye T3 law model and comparison. Yang ni saya tunjuk di paper saya buat dengan Amirul Idham. So this slide presents one of the most lagi famous successes of the Debye model. At low temperature, Debye model predicts the specific heat behavior much more accurately than the Einstein model. This one we know. We already talked about this in the previous slide kan. Daripada Einstein, kita guna Debye model pada low K and pada low temperature. We use Debye model. Very successful. So this happened because Debye model describes low frequency acoustic vibrations much better. Kan? Tengok balik graf akustik tadi tu. Kan? Dekat low frequency, low omega kan. We can describe using Debye model much better because it follows the Debye model yang ada slope tu kan. That's it. At low temperature, those low frequency modes are the most important one. So the Debye model gives the correct trend, and the Einstein model is still valuable because it is simple and we have, kita ada satu rasa macam terutang budi dekat Einstein, historically important, even though it is not really realistic, but it is not as accurate in the low temperature region. So the main comparison is this. Einstein is simple. Einstein very simple, but Debye is physically better. That is all. Kita tak kutuk Einstein sebab tanpa Einstein buat kesilapan tu, kita tak akan dapat Debye, dan tanpa dapat Debye, kita tak boleh upgrade dengan model Debye yang mana nanti paper saya tunjukkan. Especially for low temperature solids. Alright. So we never kutuk the other physicists tau. No. We appreciate what the other physicists has taught us. So we summarize the whole chapter. We started with the idea that atoms in crystal vibrate around their equilibrium position. Sama ada dia vibrate begini ke? Ini optical. Ni acoustic. Okay. So we studied the simplest monoatomic chain, one linear change with similar atoms, and saw how the lattice vibrations can be described as wave. And then we introduced the dispersion relation, the Brillouin zone, and the long wavelength limit. And long wavelength limit, yang mana Debye model tak boleh nak terangkan pada long wavelength, dia boleh pada short wavelength and small frequency and small temperature. So after that, we move to the diatomic chain and learn that acoustic and optical branches. Okay, ini adalah optical. If the frequency like this, opposite to each other. If the frequency like this, we are talking about the acoustic behavior. This is optical, this is acoustic. Then we shifted from the classical description to the quantum description and introduced phonons. Phonons is a packet of atomic vibrations. It carries the energy of vibration. And finally, we use those ideas to understand thermal properties compared to the Einstein and Debye models. So the big message for this chapter is very simple. Tiny atomic vibrations are responsible for major physical properties of solids. That is why crystal vibrations are such an important topic in material physics. So that is why also people who learn solid state physics, we have the tendency to see things better because we understand, we already learn. Small contribution of very small vibration will contribute a lot to the whole system. That is why if we have a people with dangerous mindset in our organization, one people with dangerous mindset in our organization, please do not ignore them, because that mindset will propagate, and later it will, that atom with the dangerous mindset, that people with dangerous mindset, he will have another neighbor that will have similar mindset like him. So cumulatively, they will build up a community with dangerous mindset. So what will happen to the whole system? The whole system will change. We are not against any change, but we want a positive change. So it's up to us. How do we define dangerous or safe mindset? So we have to cater those people with dangerous mindset. We intervene and do some corrections. Remember, small doesn't mean will not contribute. Small will contribute to the whole system if they have many communities. So that is all for today. Let's see. On Friday, we will discuss. Question I will upload in the column tonight. Okay, class dismissed.